Hello, welcome into today's general chemistry class. As I mentioned in class on Friday, I have to miss class on Monday, September 25th, and I've decided to record myself so that you don't have to miss any of the important information or cover it on your own. So today on the video, I'm going to pick up right where we left off last class, working on the skills of naming compounds, and then we're going to move towards learning how to predict the formulas of compounds. Right? It just occurred to me that for some of you who have me for both physics and chemistry, you're probably pretty tired of this outfit by now if you've seen me potentially for 4 lectures in it. So rest assured I'm pretty tired as well, and it's the equivalent of my 6th class of the day, since this is still Friday afternoon in real time here. So I'm going to try to do my best to be as efficient as possible. I hope that my writing on the whiteboard will be clear enough for you to see and distinguish. As I do in class, though, I'll try to be very clear in what I'm saying as I write it down. Of course, you'll have the benefit today being able to rewind if you didn't catch me say something, pause the video while you might write something down, or try even to name some compounds on your own, which I'll ask you to do in a few minutes in the video. Okay? So real quick, just so we're all on the same page, the last thing that we talked about in lecture on Friday was the system that we use, the systematic way that we name ionic compounds. All ionic compounds consist of a cation and an anion. The cation is that positively charged ion, and the anion is the negatively charged ion. So we simply name the element of the cation, and then we use the root name of the element for the anion, okay, with the suffix IDE, ide. Our exception to this pattern is that polyatomic ions are used as is. So if we have a sulfate, we keep that name sulfate. If we have a nitrite, we keep that name nitrite. We do not change its ending to IDE. So let's go through a series of examples of ionic compounds and name them according to this pattern. LiBr, MgS, K2O, GaF3, MnSO4, Be3PO4, and NaClO3. This first column, this left-hand column, these are all what we call binary. Just so you hear some more of the terms associated with chemical naming and chemical structures. These are all binary. Of course, bi is a classic prefix that means 2, and you see all of these compounds have only 2 different types of elements. These over here might be called ternary. In some circles, people would use the term ternary, which is associated with 3 or more types of elements, and you see 3 different elements. In each case, these are all ionic. And again, how do we recognize ionic compounds? They have a metal and a non-metal. That's true of all the ones that are binary here. All these are metals. How do you recognize metals from non-metals? Well, remember, in the periodic table, I'll come way over here, the periodic table has a line that clearly divides the elements that are metals from those that are nonmetals. And if you consult your periodic table, each of these has something from the left side of that line with something from the right side of that line. The other way to get an ionic compound is to have a polyatomic ion with some other element. And each of these has a polyatomic anion. So the sooner we recognize the list of polyatomic ions found in our textbook in Chapter 3, the better off we'll be. All right, let's put our system into work then. In this case, the cation is lithium. So I just used the name lithium, unadulterated. The anion is bromine. And so I'll change that to bromide. Okay? Little details, but important nevertheless for communicating correctly in the chemical discipline. Names are not proper nouns. Please do not capitalize the name. Okay? They're not proper nouns. And there is a space between the parts of the name, all right, between the cation and anion name in ionic compounds. All right? So lithium bromide. Our second one, cation is magnesium. Mg is magnesium. Anion is sulfur. The root of sulfur is sulf. And then we use the IDE suffix there. All right? So magnesium sulfide. Right? Again, here's, as I was just saying a couple minutes ago, might be a place where you might want to pause and see if you can name the other 5 on your own, and then start playing the video again and see if you've gotten them correct. See how quickly you're picking up on this pattern. This next one, the cation is potassium. And the anion is oxygen. So we just use the ox from oxygen with IDE. Okay? Don't worry about the fact that there are 2 potassiums. Once we get to the system for coming up with the formulas for ionic compounds, we'll understand that this is the only formula, the only compound that can form between potassium and oxygen, all right, in practical terms. So we don't need to say anything in the name, at least, like dipotassium. It would be unnecessary, redundant, or repetitive information. All right? So the system of ionic compounds, we understand that there's typically only one version of a compound, one formula that can result between 2 elements when they form an ionic compound. So we don't need those prefixes that maybe you've heard of in other situations. All right? There will be a few special exceptions in a minute that I'll highlight and tell you what we do with them. So this next one we have Ga, that is gallium. And then fluorine is our anion, so it is fluoride. Okay? Gallium fluoride. Okay. Okay. Over here in our second column, now we have some polyatomic ions. All right? Nothing changes about the system except that we use the polyatomic ion name without changing it. So we still need to name our cation here, which is Mn this time, so that is manganese. And then that was on our first exam. I know, and several people had some interesting spellings of that. So manganese. And then this SO4 is called the sulfate ion. So we just stick with manganese sulfate. All right. The next element we have is beryllium. This was one that I had to accept lots of alternative spellings for on the first exam. Beryllium, B-E-R-Y-L-L-I-U-M is beryllium. And then the PO4 is the phosphate polyatomic ion. All right. And then our last case here, Na is sodium. And the ClO3 is another polyatomic ion. All right. It's part of that family that we looked at last class that has 4, but the ClO3 is the chlorate. ion. So that is sodium chlorate. All right. All right. Now, there are a small group of metals in the periodic table that are known as being bivalent. That means that they are metals that can have two different ionic charges. This isn't true for metals like lithium, magnesium, potassium, gallium. Their charge is dictated by where they are in the periodic table. As a group 1 element, lithium must have a +1 charge. Potassium, also group 1, +1 charge. Magnesium, group 2, has a +2 charge. However, several metals can have two different possible charges, and they're usually transition metals. So we have to be on the lookout for chromium, because it can be +2 or +3. Okay, +2 or +3. Iron can also be +2 or +3. Cobalt can once again be +2 or +3. All right. Copper would be possibly +1 or +2. That was part of the mystery in lab last week, identifying the empirical formula of the copper-sulfur compound, because we're not sure which version of copper we were forming when we took our elemental copper and turned it into an ion, right? And so you had to go through the exercise of weighing out your copper carefully and weighing out the product afterwards to try to determine which form you had. Tin. Tin, Sn is its symbol, can be +2 or +4. +2 or +4. And lead can also be +2 or +4. Mercury is also bivalent, but we are not very likely to encounter mercury. Okay? So how we handle this bivalent component when we encounter one of these metals is by indicating its charge as part of the name. Okay? So we'll use the charge, use the ionic charge as part of the name. Before I can show you that, though, I think I need to show you how we come up with the formula of an ionic compound so that you'll understand how to figure out the charge, which charge you have actually. All right? So we're going to be sort of jumping back and forth between names and formulas right now. The formula of an ionic compound is determined by ensuring that we have a neutral molecule overall. Okay? So although it's not really a molecule, honestly, of an ionic compound, but if we thought of it as a single unit, we call it a formula unit more accurately. But for right now, I'll just use the term molecule because we've been familiar with using that so far this chapter. So in a molecule of an ionic compound, the total amount of positive charge positive charge, where's that coming from? It's coming from the cation. equals the total amount of negative charge. And that negative charge comes from the anion, right? So when we consider putting together two elements to form an ionic compound, we need to know what their potential charges are. All right? So excluding these bivalent compounds for a second then, if, let's say, if magnesium bonds to chlorine, magnesium forms a 2+ ion. Chlorine forms a 1- ion. So if we attempted to put one each together, we would not have a neutral molecule. We would have an excess of positive charge. In a simple case like this, it becomes pretty obvious, right? Oh, we need 2 chlorines, each of which are -1, to balance that 1 magnesium that's +2. And that's where the 2 would come from. But there's a simple way to predict that for every compound. And so if you learn it with these simple molecules, you could use it for more difficult cases reliably. All right? Essentially, if we cross the charges down to become subscripts and then reduce, we would get the correct ratio that ensures that we have a balanced molecule. What we're really doing is saying if we multiply -1 times 2, we have 2 units of negative charge. If I multiply +2 times 1 magnesium, I have 2 units of positive charge, and you see those have canceled or equal one another, which is what's required for an ionic compound. So the way to get the formula, the way to predict the formula, is to write the symbols of the elements with their ionic charges. Okay? And then you want to make sure that you write the cation first. And then you switch the ionic charges. So each charge becomes the subscript of the other element. And then you would reduce, if not already, the lowest whole number ratio. Okay? Ionic compounds are always written with the lowest whole number ratio. Okay. So if we had a couple examples here, how about calcium oxide? How about potassium chloride? And let's throw in a polyatomic ion, maybe aluminum nitrate. I'm going to start with the middle one, potassium chloride, first, actually. It's the simplest case here. Write the symbols. Potassium, that's 1+. Chlorine, that's 1-. Cross those symbols down to become the subscript of the other element. Because these are 1 to 1, we need 1 potassium to offset one chlorine, and the final formula is simply KCl. Right? In the case of calcium oxide, though, calcium is a 2+, oxygen is a 2- ion. Again, where are these coming from? The groups that these elements belong to. Calcium's in group 2, so it becomes a +2 charge. Oxygen is in group 16, so it becomes a -2 charge. Crisscross these charges, swap them down, and it looks like we have a temporary formula of Ca2O2. But ionic compounds are always reduced to the lowest whole number ratio, so this would become CaO, and that's your formula for calcium oxide. Okay? Aluminum nitrate. Aluminum is an element in group 13, so it has a +3 charge. The nitrate is a polyatomic ion, NO3, with a 1- charge. If I swap this down, it starts to look a little confusing. We've got Al, NO3, 3. This second 3 is defining how many of the nitrate groups we need, right? This is a cluster. You could almost treat this as Al3 plus X, 1-. And you can see a little easier, you'd need AlX3. X is nitrate. Since it has a little subscript like that, we're in the habit of using parentheses if there were 2 subscripts that needed to be side by side. All right? That's the only time you need parentheses. If we did this with magnesium sulfate, actually I'll change that to sulfite. Magnesium is Mg2+, sulfite is SO3 2-. It looks like a temporary Mg2 SO32, but again, that can reduce, and it would just be MgSO3. And I wouldn't actually need the parentheses around the sulfite in this case, because I have only one sulfite group there. Excuse me. All right, now how does this help us with these bivalent metals that I still have drawn on my board over here? So now we have to think about this process in reverse. All right? If a metal that we know to be bivalent shows up in a compound like CuCl or CuCl2, all right, it has its 2 different charges here. And how do we figure that charge out? Well, we can work backwards from this formula to what the charges were, right? These 1s come from the fact that the copper was a +1 and the chlorine was a -1. In the other example, if we uncross the 2 on chlorine, it came from the +2 that was copper, and again, -1 on chlorine. So here we have the copper 1+ ion, and the way we incorporate that into the name, because this is an ionic compound, it should be copper chloride, but these can't both be copper chloride, right? They need different, distinct names because they are different, distinct compounds. So we put a Roman numeral 1 after the copper, and then we finish the name as usual. This Roman numeral 1 is the ionic charge. It is not how many coppers there are. It happened to agree in that case, but you can see over here it doesn't agree. So proof of that principle. This is called copper 2 chloride. because of the copper being a +2. All right? So it's a Roman numeral indicating the ionic charge. Some of these can be a little sneaky. Let's stick with copper. CuO. This looks just like the CuCl case. If we uncross it again, boy, it sure looks like copper is a +1 again. And we're all set to say this is copper 1 oxide. But that doesn't work because oxygen is not actually a -1. This is an incorrect charge on oxygen. The real charge of oxygen is -2. So if the real charge of oxygen is -2, the real charge of copper must have been +2 because they scale up or down together. So what really happened here was that Cu2+ bonded to O2-, those crisscrossed down. We got that 2-to-2 relationship, which was reduced to 1-to-1. So this is, in reality, copper 2 oxide. And so it's really important that you know the charges that certain elements, particularly your anions, should have, so that you don't misdiagnose one of these charges that we have. Okay? Let's do one more here. How about Fe2CO3 3. All right? A lot of numbers going on there. These come from then, these subscripts came potentially from ionic charges. A 2- looks like on CO3 and a 3+ on iron. What do we know? This is one of the possible charges of iron. Iron can be +2 or +3. But we should double check. CO3 2-, that's correct. That's called the carbonate ion. So we've identified the correct charge on that ion. So now we can go ahead and name this as iron 3, because that's its ionic charge, carbonate. All right. So these aren't that common. They don't show up too often. So I don't want you to get too worried about these. But nevertheless, this is how you handle these bivalent metals. All right. You use their name, you add this number to their name. As far as finding the formula, well, if you were given the name, it's pretty obvious then. When you see iron 3, that becomes the charge that you use in the crossing down method. All right. All right, let's move on to our next category of materials to work with, or compounds to work with. That's going to be molecular compounds, or covalent. Now, those are two names, really the same thing, but covalent, you may also hear the term molecular compounds. All right. The names, since we did names first for ionic compound, okay, names follow this model. Again, there's a model, a system at work. There is a numerical prefix, okay, then attached to the name of the first element. Then you would need another numerical prefix, the root name of the second element, with the suffix IDE. So just like the ionic compounds, for better or worse, all of these end in the name IDE. Okay? There is one exception to this that I'll list the prefixes that we need in a second. We do not use the prefix mon on the first element. Okay? So if the first element has only one atom, we would not use this prefix mon. So what are these prefixes that we have? If you have one atom, you do use the prefix mon, except, as I just said, on the first element. All right? You wouldn't do that. If you had 2 atoms, you would use di. If you had 3 atoms, the prefix is tri. If you have 4 atoms, the prefix is tetra. 5 atoms, it is penta. Continuing, I'm just going to add room there. 6 atoms would be hexa. 7 atoms would be hepta. 8 atoms would be octa. 9 would be nona. And up to 10 would be deca. So we're going to use these prefixes to indicate how many atoms of any element are present. I'm going to have to pause my video right now. Looks like I'll need to move to another location since a class needs to come in and use this space. And I'll merge it with the second half of the video that I make. So there'll be a little brief interruption here, but I'll continue this thought in just a minute.